Hello students, Professor Nugent here. In this video, we're going to discuss the simple regression model. We're going to define the simple regression model. In simple terms, the simple regression model is a method for studying the relationship between two variables, x and y. We define the simple regression model as follows. Y equals beta naught plus beta 1 times x plus u, where y is the dependent variable, x is the independent variable. Beta naught, this is the intercept, if you will. Beta 1 is the slope, and u is the error term. Included in this error term is stuff that is unobserved, that affects y, and is unrelated to x. Let's call this equation 1 and talk about equation 1, further define equation 1. Alright, so equation 1, the simple regression model, defines the functional relationship between these two variables, x and y. That is, the change in y is given by beta 1 times the change in x. So there's a linear relationship between x and y. Let's call this equation 2. Alright, and what does equation 2 tell us? That is that the change in y is given by beta 1 times the change in x. Beta 1 represents the change in y for a 1 unit change in x. Alright, so we'll talk about beta 1 as the slope, right, as we just discussed, or the coefficient on x, which tells us how much y changes for a 1 unit change in x. Let's look at an example. We're going to talk about the relationship between wage and education. You might be able to predict a person's wage based on their level of education according to the following model. Alright, so you may be able to predict wage in terms of dollars per hour using the following equation: beta naught plus beta 1 times education in terms of years plus u. How would we interpret beta 1? Well, let's look at the analog to equation 2. Change in wage is equal to beta 1 times change in education. So beta 1 gives us the increase in wage in terms of dollars per hour, or so that's our hourly wage, for an additional year of education. If you want to look at an increase in the level of education by 2 years, you'd multiply beta 1 times 2, and that would give you the predicted increase in wage. Now, importantly, this relationship is under the assumption ceteris paribus, which means, this is Latin, it means in English, all else equal. When we say all else equal, what do we mean in terms of our equation? That's delta u equals 0. What might be contained in delta u? Things like ability, alright, or experience. So we want to hold all of this other stuff constant. Look at two individuals with the same ability, same level of experience, but two different levels of education. What is the resulting differential in their wages? All right. Now we are making the important assumption that ability and experience are unrelated to education, but they do affect wage, and they are unobserved. We will, later in our video series, discuss the implications of this assumption. Let's further define our model. Okay, now let's discuss this error term u. The expected value of u is 0. Call that equation 5. This tells us that the errors above and below our predicted line average out. Okay, so that we have a mean of 0. Next, let's talk about the relationship between u and x. We have this idea of mean independence. That is, the expected value of u given x is equal to the expected value of u. All right, call that equation 6. When we put together equation 6 and 7 together, we get the 0 conditional mean independence assumption. Now this is an assumption. We are assuming that this holds. That is, that the expected value of u given x, because it is equal to the expected value of u, it's equal to 0. All right, so the mean of u is 0, and that holds when we condition that on x. So whether you look at different slices of the domain of x, you're still going to see that the mean of u is going to be 0. Let's look at what we mean by this on a plot. Okay. Say that we are still looking at predicting wage given different levels of education. And this line might represent our regression line. And let's assume that we have 3 different levels of education: level 1, level 2, level 3. Maybe level 1 represents high school, 2 bachelor's, 3 grad school. We are assuming that the distribution of wage at each slice of education is the same. All right. So we have something like this. In other words, the deviations above and below the line are assumed to not be related with higher or lower levels of education. All right, let's think about this even further. If we define, make some space here. This variable ability, abil as is ability, and we say that this is unobserved. It's not easy to observe quantitatively an individual's ability, whether they are low ability or they are high ability. It's hard to observe that quantitatively. Ability will be important for an individual's wage, right? The higher the ability of an individual, the more likely they're going to get higher performance reviews and get better raises. So ability matters for wage, so it is contained in that error term. By this zero conditional mean assumption, we are assuming that higher able individuals, or rather that ability is unrelated with different levels of education. That you have the same distribution of ability over the different levels of education, which might be a bad assumption, because you might expect individuals that get higher levels of education, like masters and PhD and MDs and all of the other post-secondary higher levels of education, to be of higher levels of ability. So you might expect there to be a relationship. But this zero conditional mean assumption says that no, they are not related. So the expected value of ability given, say, education equals 1 is going to be equal to the expected value of ability given education equals 2, which might be equal to some constant. It is some unobserved constant. Why is it a constant and not 0? Well, folks, this is just one of the very many unobserved factors that are contained in U, which altogether average out to be equal to 0. So this constant might be a positive constant. Then you might have another unobserved factor that is a negative constant, and together they average out. That is what we are assuming, so that our model works and that we can make useful derivations and have consistent unbiased estimates. All right. Now, if we put together equation 1 with equation 6, we can come up with our population regression function. All right, equation 1 plus equation 6. So equation 1 is a simple regression model. Equation 6 is the mean independence assumption. Let's put these things together, and we get that the expected value of y given x is equal to beta naught plus beta 1 times x. The expected value of y, which u is a part of y given x, is equal to 0, so that term falls out. All right, so this is our population regression function. This is a population relationship for how y changes on average with x. Beta naught and beta 1 are the population parameters. All right, folks. So that, in sum, is the definition of the simple regression model. Thank you.